Welcome back to ECE 220. Today we're going to look at step responses of RL and RC circuits. And just as a reminder, the last section in Group A, your lab number 3 is today. Lab B, your pre-lab is due Saturday. And your lab 3 is next Tuesday, as is homework number 9. And Group A, your report for lab 3 that you are finishing up this week is due next Wednesday. As an announcement, a week from today we will not be holding class physically here, and the following Friday we won't be holding class. So you're going to have at least 2 Fridays off, and I think I've already committed to the Wednesday prior to the Thanksgiving break will also give you off. So there are 3 dates that you can now plan around or plan your schedule with. And Group A, sandwiched between all of that, your pre-lab for number 4 is due a week from tomorrow. It's due on Saturday, the 2nd of November. Our exam, number 3, is 2 weeks from yesterday. It's now on the 7th. It's Thursday, November 7th, and that will be covering the op amps and the inductors and capacitor material in Chapter 5 and 6, which is homeworks 7, 8, and 9. And 9, again, homework 9 is due this coming Tuesday. What we want to do today is start pushing these circuits, meaning let's just excite them with constant inputs. It's now the step response of these first order circuits. This is coming from section 3 in chapter 7, and you might hear this called a forced response with DC sources, etc. We'll work through that process, stepping through how do we find the solution, and we'll actually just abbreviate it with an acronym. Because we are dealing with constant sources, the solution structure is fairly clean. It's FIFE. So final, initial, final, exponential. That's how we will remember the generic structure, which means we need to find the final value of our state variable, the initial value of that state variable, and the time constant, and then we'll have the solution because we will have known the structure. We'll derive that structure today, and then we will work through some examples and try to develop our intuition into how these circuits are going to behave. Here's what we are looking at. Generically, on the left we have this RL circuit, a resistor in series with an inductor, and we have an RC circuit. The generic one, let's say, is now with a current source, and so now we have this Norton source driving a capacitor. We have a Thevenin source driving the inductor. But we now want to examine what happens when these systems now are excited with a constant waveform starting at, let's say, sometime 0 or t sub 0. T sub 0 might be 6. It might be 2. We might not be turning this on right at or at 0, but we need to switch it on. And we'll try to, probably most of the time, we'll just say the switch is happening at t equals 0, because really we can kind of draw the line in the sand as far as what is our t equal to 0, or what is our starting time, or when does that switch occur. We'll just say, oh, that's happening at t equals 0. If we are confronted with an RL circuit, a resistor inductor circuit, what variable do we want to focus on? We want to focus on something, something. And we might think, okay, what's our energy storage element here? It's only an inductor, so we can fill in one of those blanks. That one was sort of given. Focus on inductor. Now what do we focus on? Current or voltage for the inductor? And if we recall how we're trying to remind us of all these relationships, we can go back to Eli. Eli ends with an I, and that's the one we focus on. That's our state variable. So we're going to focus on inductor currents when we have an RL circuit, where this is now our state variable. And with ICE and a RC circuit, we now want to focus on the capacitor voltage. Where the capacitor voltage is now our state variable. And that means if you know the state of that variable, you basically know everything about that circuit. That's why you can refer to it as a state variable. Let's look at this for one of those two scenarios. Let's just look at the RL circuit. That says Eli, so now we're focusing on inductor current. And instead of putting more circuit apparatus around this to establish the initial condition, let's just say that we are going to state what the initial condition on that inductor current is. Let's just say it's something not equal to 0. We want it to have some current at time 0. And we could do that by switches and sources, but let's just say, let's clean this up a little bit and only worry about the circuit after time 0, and let's just assume then that the current through that inductor is something other than 0 at time 0, or the initial condition we'll just call I of 0. We can then write the governing equation that describes the dynamic behavior of that circuit after time 0. When the switch is now closed, we now have this series RL circuit forced by a constant input, and we're assuming we know capital V of S. We're assuming we know what that battery is, or what that voltage source is. V sub S is 10, it's 50, it's something, but it's a fixed constant. We know capital V sub S, we know the initial condition. We can write KVL and rely on Eli to give us that L di dt. That's the voltage dropped with the passive sign convention, consistent with the way that we've referenced the current direction. This is now minus V sub S plus voltage dropped across the resistor is Ri, plus the voltage dropped across the inductor is L di dt. That's a first order ODE. You'll see this many different ways, or referred to many different ways. It's an ordinary differential equation, and in fact this is linear, isn't it? We don't have any products of variables, or we are not exciting this source with some nonlinear behavior. So, and I and DI, those are all coming in linearly. This is now a linear system. We can then rearrange that governing differential equation. Again, I'm just reminding us that V sub S is a given constant value. We can isolate our derivative, and now what we want to do is use this first order differential equation to find the solution for I, the current in that inductor, for time after the switch has been closed, for t greater than or equal to 0 in this case. And we're going to do it maybe a little differently than what the book did it. Let's just do the two-part solution to these ordinary differential equations. Let's just break it up into two pieces, a homogeneous piece and a particular piece, and sum those up to get the complete solution. The homogeneous piece is when we shut all the sources down. We have the system just with the natural behavior of the system, no sources present. So we'll obtain the structure of the homogeneous solution, and we'll call that, if we have an RL circuit, we'll say that's I sub h for the inductor current. The homogeneous is the subscript. If we're working with an RC circuit, we're concentrating or focusing on the capacitor's voltage. We'll subscript that voltage with an H for homogeneous. We'll then find the particular solution, call that I sub p or V sub p, respectively. And then we'll go ahead and compute or find the complete solution using the initial condition. That's step 3. So it's really a 3-step process. And as I said, once we've done this, since in this class we will be focusing on constant excitation or forcing functions or constant inputs, we'll be able to just say phi final, initial, final, exponential, and write down the structure of our solution. And eventually then just find, by inspection of our circuit, what the initial condition is on that state variable, what the final value is on that state variable, and what's the time constant to provide us with the exponential structure. Let's work through that now, and then we will use this in our toolkit, but we won't necessarily have to always rederive this as we go through it. Now, for step 1, we set the sources to 0, so we're not having that capital V sub s, and we want to now determine what is the structure of our homogeneous solution to the homogeneous equation. What's the structure of our homogeneous solution? And this looks like what we were playing with in the first part of chapter 7, which is the natural response. We had dx equal to minus x, or something x. Or here we have di dt is equal to minus r over L I, or we could lump those two parameters into a new parameter called our time constant, tau, and now we have di dt is equal to minus 1 over tau I, where this tau is our time constant, which in the RL circuit is L over R. And we know what the homogeneous solution is. That's what we were dealing with the natural response. I sub h, which is what we said we would call it, what does it look like structurally? If I now say I have something whose derivative looks like the something, what did you tell me that functional structure was? An exponential. And in this case, since we have passive circuits and our resistors we're assuming right now, we don't have any dependent sources, we're assuming our resistors are positive, we now have a dissipative system, so that exponential is actually going to be negative. The structure then of this homogeneous solution is now a e to the minus t over tau. And what we want to keep in mind now is We can find the tau, we know what that is, but we don't want to yet find the constant A. We want to wait until step 3 to determine what A is actually going to be. We'll then solve for A. That constant, that's just a constant, in step 3. And definitely not now. And you'll see this homogeneous solution written many different ways, but we always want to, right now, at the conclusion of step 1, is just keep A as an unknown constant. We have A e to the minus t over tau, where tau was L over R, or you might see it then as e to the minus RT over L. And our switch, we were turning that on at 0. In this case, then, our exponential behavior for the homogeneous is going to be valid for t greater than or equal to 0. We're done with step 1. The particular solution, that's particular to the structure of the source that you're applying to your system. And in this class, so far, in Chapter 9, we'll start exciting these with sinusoids. But then we'll sort of go into the frequency domain and not have to worry about differential equations so much. But for now, when we're talking about time domain response and time domain solutions, we're dealing with constant inputs. The particular solution is going to have the same structure as that excitation or forcing function, or the constant waveform that we're exciting the system with. We hit it with a step. We would expect everything after all the transients are gone to be constant in our circuit. That's what we're meaning. We are going to now have the same structure for our particular solution, or it's going to be consistent with the forcing function structure. And that's what I'm trying to say here. The particular solution structure is generally, and that's where you'll learn more about this later when you now start exciting the circuit with an exponential, and maybe that exponential is actually one of your natural modes of your circuit. Then you have to start doing a little bit more to find your structure of the particular solution. Here, we just are going to assume that our structure for the particular solution is a constant, since that's how we're exciting our system now, with a step. So we're going to let I sub p be B. B is another constant. We're just working our way through the alphabet. Step 1, we used a constant A. Step 2, we're using a constant B. And now what we want to do is we need B. That's a constant, but we now need to find that in step 2. So B needs to satisfy the governing differential equation. And in step 2, we're back where we originally started, with the source being present. So B needs to satisfy the governing differential equation with the source present. Or we now have this differential equation. We're trying to find I sub p. We know this I sub p needs to satisfy our governing differential equation, which is di sub p dt is minus L over R I sub p of t plus R over L plus 1 over L V sub s. That's what I sub p needs to satisfy. That's our governing differential equation, and that came from KVL in our circuit. di dt is minus r over Li plus 1 over L v sub s. And as a reminder, let's just note or recall that in this differential equation, v sub s, that's known, or that's a given constant. We don't have to worry about what that is. It's just going to be given to us. 10, 20, 50. V sub s is just a constant voltage. Now, we said we wanted the structure of our particular solution to equal a constant b. So if we now let I sub p be b, we're taking the derivative of b on the left and setting that equal to minus r over lb plus 1 over L v sub s. We differentiate a constant, that goes away, that's 0. Now we have 0 equaling minus r over lb plus 1 over L v sub s. We can multiply both sides through by L. That cleans it up a little bit. We can move we can add RB to both sides, and now we have RB is equal to v sub s, or now we know what b is, that constant that we were trying to find. Solving for it is now v sub s over r. V sub s was a given, and r we're assuming we know. That's the resistor in our circuit. Now we know our particular solution. I sub p of t is now b, and we've now found b. That's now v sub s over r, and that's what the particular solution is for all time beyond 0. We have our first step and second step. Now we're ready for the third step. The third step is to put these first two steps together to give us the complete solution. That's now I of t. The inductor current is the homogeneous piece or part plus the particular part. The homogeneous was a e to the minus t over tau, and the particular we just found was v sub s over r. That's now the structure of our complete solution. And we know that we had a non-zero value for the current flowing through that inductor. This was given. We can now use that initial condition to find the only remaining unknown in that expression, which is capital A. Let's now then do that. We now have that complete solution at time 0. So we now know I of 0 is equal to a e to the minus 0 over tau plus v sub s over r. Or this is now a plus v sub s over r, and we can now solve that for a. Giving us our solution, complete solution that we want. I of t is now a, which is I of 0 minus v sub s over r. That's a times our exponential structure, e to the minus t over tau plus the particular, which is plus v sub s over r. And we're going to just rearrange those, just exchange the order of the sum on the right so that we can use that acronym to remember how the structure of this looks. We'll pull v sub s over r first, then we'll add to that the constant that scales our exponential. And here our switch was occurring at time 0. So this complete solution is now true for t greater than or equal to 0. And what you can maybe see is that here is our final value of the current. Here is our initial value. Here is our final again. And then we have this exponential, which means if we just extract the first letters of those 4 words, final, initial, final, exponential, we have a mnemonic way of recalling or remembering the complete solution for a step response RL or RC circuit. We now have FI, FE. Final, initial, final, exponential, and this is what we can rely on to provide us with the structure of a step response solution. That's because we were assuming we were exciting this system with a constant. And now this structure presents itself to us. If I now say, oh, what's the structure of this RL circuit's solution to a step? You just say phi and write down, oh, I know it's the final plus parentheses, initial minus final, times an exponential. Then what do you need to do? You need to find the final value of that current, its initial value by inspection of the circuit, and then find the time constant. And now you'll have the complete solution available to you. Let's go through an example and see if we can make this more clear than I hope it's already crystal clear. But let's look at an RC example. Suppose let me go ahead and do my switch here. And I'm trying to emphasize that I have constant sources by drawing these DC type sources. Let's say that this is now plus 5 volts. Let's say the one on the right is 12 volts. And just to give it a little more character, let's say that these switches will occur at time t sub 0. And let's say our resistor on the left is 5, the capacitor is 1, and this resistor, let's say, is 2. You're now presented with this circuit, and you now need to find its complete solution. What would be your first thought in terms of, okay, what variable do I need to now try to be solving for or working with? What's my key variable in this circuit? And now you can see that you really have two distinct circuits, one before T0 and one after. These switches I hope I've labeled as going in opposite directions at T sub 0. Before T sub 0 we have the circuit on the left. After T sub 0 we have the circuit on the right. What variable should we focus on? I don't know. I don't really want to focus this morning. I don't either, but we need to solve it. So which one is it? Actually, I do want to focus. We've got a capacitor. What's its state variable? Now you just have to write down ice. It is kind of cold in here. You should know that, right? It's ice that we're talking about now. And that's a capacitor, and ice is E, or voltage, so we need to need to worry about that capacitor voltage. We're going to focus on capacitor voltage. That's our state variable. Let's now find limiting values on that state variable. By that I'm meaning we have two scenarios. One scenario before T sub 0, one scenario after T sub 0. We now have two limiting conditions because we're always exciting this with constant sources. And we know what happens to a capacitor when we excite it with DC sources. It opens up after the transients. So we want to find limiting values of V sub C of t. Suppose we now look at what's going to happen right before we throw the switch. And now the circuit has reached steady state, or before, now we have t less than t sub 0 as the we have that circuit. Here's 5. This was 5. This was 1. What happens to that capacitor if it's confronted with this circuit? And now it's been in this condition from time minus infinity up to t sub 0. What happens, or what's this? We now said we're focusing on V sub C. What happens to that capacitor? It's now in a steady state, this circuit. It's excited by a constant input. What's the capacitor do? It charges up, and what does it do when it's fully charged? What happens to these variables? What happens to the voltage? Is it kind of rocking back and forth? It's constant, isn't it? What happens to the current? It's 0. So this capacitor opens once it's reached steady state. So in steady state, which is what we are, the capacitor opens, and now we effectively don't have it. We now have something like this. And we want to know what is V sub C at the left side of T sub 0, right before the switch. It's in this condition. This is now 5 volts. Here's R sub S of 5. We could do KVL around that mesh, and we see, I hope, KVL gives us minus 5 plus nothing dropped across R sub S. There's no current flowing, plus V sub C of T sub 0 minus, or we now know that V sub C of T sub 0 minus is equal to 5 volts. That's now our I in phi phi. That's our initial state in the phi phi acronym. What happens at infinity? And we'll get just kind of loose and we'll just say, I want to know what is V sub C at infinity. And we now know, since we're in the know, that doesn't take very long necessarily, does it? After the switch happens and we have this system excited with constant sources, how long do we have to wait? 5 time constants, 5 tau. Then we're down to e to the minus 5, which is less than 1% of where we started. At this condition, for t greater than or equal to t0, now we're on the right side of our circuit. We have a capacitor, same capacitor, a resistor, but now a different source. But the analysis is the same, isn't it? Now we are going to be in steady state. After 5 time constants, we'll be there in steady state. We now know that the capacitor is going to open. And we now know that V sub C at infinity is 12 volts. That's now the F in phi phi. So now with phi phi, we can write down our result. We know that the capacitor voltage, V sub C of t, is the final V sub C of infinity plus the initial, that's the I in phi phi, V sub C, and in this case our initial is just to the left of the switch happening. We're going to call that F sub C of T sub 0 minus the final times the exponential e to the minus T sub 0 over tau. Since we're throwing that switch at something other than times 0, we have to shift that argument in time to T sub 0 so that at T sub 0 we do have this term being 1. And this is true for all time t greater than T sub 0. Yeah, but we didn't calculate tau. We thought we were done. We're almost there. What is tau? That's our time constant. And we need to find that for t greater than or equal to t0. We now have our circuit. How do we find tau? R times C, and if R wasn't staring us in the face, if it was more complicated, we would look back into or at the rest of the circuit through the terminals that are connecting the capacitor and say, what's the effective resistance I see standing in between terminals A and B? In this case, it's clear. You look back and you set the sources equal to 0. You now are saying, oh, what does that capacitor see? You zero that source. Here's R equal to 2. You now know what R is. R is 2. But if it was some other interconnected mess, you would still do the same thing. You would say, let me remove the capacitor and see what the resistance is looking from those two terminals. That's why we were always looking for these equivalent resistors in the past. Now we know what R effective is. That's R, which is 2, and now we have tau. And we now know what V sub C of t is. V sub C of t was our final value of voltage, which was 12, plus the initial value, 5 minus the final, e to the minus t over tau. And that was true. Oops. Stay focused. E to the minus t minus t sub 0, since we were doing this switch at some time other than 0. So we had to shift the time argument in that exponential by whatever t sub 0 amounts to in our circuit. And we didn't specify that. But now you can tell me a lot about this, and you can actually see, I hope, what V sub C of t looks like. This is now our solution to this circuit for time t greater than or equal to t sub 0. What is the length of our the transient? How long do we have to wait until we get into the limiting value of V sub C after t naught? 10 seconds, which is 5 tau. So now we have 5 tau, which is 5 times 2 in this case. That's a pretty slow electrical system, so we have to wait 10 seconds. Or we can now say that V sub C of t is 12. We can do the algebra inside the initial minus final to get 7, e to the minus, and we could say 0.5 t minus t sub 0 for t greater than or equal to t sub 0. Or you could just say minus the quantity t minus t sub 0 over tau. Here we just push the tau into the numerator by the appropriate division. And now you know what the exponential piece is. It's 1/2. That gives you the decay. Now you have your e to the minus 1/2 t shape, or what does V sub C of t look like as a waveform? It started where? Before t0, where was our voltage? You could actually use the expression, but here you know it's at 5, right? And it's going to go to 12. So you can immediately put down those two. If you say, oh, here's t0, now you can say, well, I'm 5 here, and I'm 12 here. And what happens between, or what is the distance between? We now know this transient interval right there. If that was right above, I should have made it a little better than that. This is now t sub 0 plus 10. And we now know what this is. That's our exponential. Here's our transient. That's 10 units long. And the voltage is continuous. We start at 5, and then we exponentially increase to 12. What's the current look like in our capacitor in this example? What is I sub c of t? And here I'm saying I sub c, if this is now our voltage, there's I sub c. Just to the left of, or right before we open that switch, what is the current associated with that capacitor? Or what's the capacitor doing before we open the switch? It's open, isn't it? It's an open circuit. So now the capacitor is open, and our circuit looks like that. And now if we said, well, here's our I sub c, that's nothing. So we have zero current to the left of t sub 0. We're in steady state. We now know I sub c to the left of t sub 0 is 0 amps. But now we have to worry a little bit more now, because this current in the capacitor is not necessarily continuous. The voltage is. That's a state variable. The voltage of that capacitor at t sub 0 minus and t sub 0 plus is the same. It's 5. We don't know that for this current. It might jump wildly. It's starting at 0. What is it beyond that? We now know, let's just refresh what I just said. Recall, V sub c of t sub 0 minus is V sub c of t sub 0 plus, because voltage on a capacitor cannot change instantaneously because of dV dt. This was 5. So now if we say, well, after we throw the switches, we have our capacitor, we have this resistor, and now we're connected to the 12 volt source. This is now at t sub 0 plus. This was 2. And we now know that this is 5. This is right at t equal t sub 0 plus. And we want to know what is I sub c of t sub 0 plus. We know what it is at t sub 0 minus. What was it? There was no current flowing, was there? Now, wait a minute. We have a voltage dropped across a resistor. We know what happens there, Ohm's law. We now do have a current instantly after that switch flowing through our capacitor. At t sub 0 minus, we were nothing. At t sub 0 plus, we've now become something. What is the current? What is I sub c of t sub 0 plus? We have a lot of subscripts, superscripts. You have to keep them all straight. I sub c t sub 0 plus. That plus you could tell was an X in the superscript. What is this? All right. You just, oh my. Look at the time. But isn't it 12 minus 5 over 2? It's the voltage dropped across that resistor. 12, that's where we are, 12 to 5, because we're having the current going that way. So this is now 7 over 2, or 3.5 amps. So what just happened? I'll sort of do this for you as you're exiting and cleaning up, but we had nothing here. This was I sub c of t. Then what happened? Then we jumped up to 3.5, and what happens at the end? Way off into the future, that current goes back to 0, doesn't it? And the exponent is going to have the same exponential shape that we've enjoyed in this exercise, or in this particular example, and that's now our current. It's discontinuous at t0. We'll pick up with a lot more switching, I think, on Monday.